Good afternoon, everyone. We're going to get started by creating a quick equation that would describe this situation. We want to represent the cost of getting a cell phone if the monthly fee is $30 and we have to pay 2 cents per minute of call time. So can you create a function that would do that? And then tell me the domain and range of that cost function. Okay? So we have this one on your handout. It's on the back, and it's the last question that we're going to look at, okay? So you can go ahead and take a look at this question on your handout and kind of sketch it. It's on the back of the first page. I actually have 2 pages worth of handouts there stapled for you. It's down here after determining values from a graph. It's down right here. Okay. So find the domain and range for this cost function. All right. So you can go ahead and get started on that as I'm working away. And I'll warn you when we're going to be doing things on the handout as well on the first page. So we want to remember a few things about about algebra particularly. And those are the distributive property is about when I have some number multiplied by a bracket that has a binomial in there or even a trinomial. I'm going to distribute that monomial across the polynomial inside in this way. A times B would give me AB, A times C would give me AC, and then when I add those together, those two things are the same. Okay. This is like saying there's a banana and a coconut inside a box. If I have A boxes, let's say I have 3 boxes, well then I would have 3 bananas and 3 coconuts. Okay. So, thank you very much for showing up for your learning. And then after we do this type of expansion, we want to remember that we can collect like terms. This box has apples and $4. This box has apple and $2. If I have 4 of those boxes and 3 of those boxes, well, I would have a total of $20 and 7 apples. Function notation. This is something we're going to use all year. You want to get very comfortable, very good at using function notation. We're going to do that today. We're going to have a quiz on it tomorrow, and we want to use this every day. It's a new way we're going to write functions. All right? So let's take a look. Here is a situation that gets confusing when you don't have function notation. Imagine you have these 3 lines. Y is equal to 2x plus 1, y is equal to 2x plus 5, and y equals 1/2 x plus 4. So we see there's one solution there to these 2 lines. There's going to be another solution over there with this red line and this blue line. The blue line and the green line, will they ever have a solution? Will they ever touch? No. Why not?
Because they're parallel.
Because they're parallel. They have the same slope. Yes, very good. So that's good. Your y equals mx plus b game is strong. Your y equals mx plus b game is strong. The problem is, if I want to specify that I'm talking about one of those lines, it can be very difficult to refer to an individual function. For example, how would I talk about this idea if I wanted to say, for this line here, y is equal to 2x plus 5. It has a y value of 9 when x is equal to 2. Okay, it's very wordy. It's very long to say something like that because you see I have to first specify I'm talking about this line. And then I have to specify, look at this x value of 2. And then I find that I have a y value of 9 up there somewhere. This is wordy. I could talk about its y-intercept to distinguish it from other lines, but maybe it has the same y-intercept as another line. I could color code, but color coding is annoying and it's difficult because I might be publishing in black and white. So that wouldn't be very useful. A better situation is to use function notation. And we're going to use function notation to distinguish these different functions from one another right inside the equation. Okay? Over here, you'll notice that all the equations are like y equals y equals y equals, right? Now we're going to use function notation to do that in a new way. And so here it is. And this is on your note over here. Function notation uses a letter as a label, followed by a list of all variables that the function depends on. Okay, so we're going to be seeing familiar equations, but they're going to be followed by, but they're going to be preceded by function notation here. And the way we read this, so you want to be able to read this very effectively, like fluently, I mean. For example, the notation f of x is equal to, f, and then we have this bracketed x is equal to 2x plus 5, okay? We read this like this. F of x equals 2x plus 5. F of x equals 2x plus 5. So now I'm going to read that, and you're going to say it out loud after me like it was a language class, because this is very much just like a definitions class here. F of x equals 2x plus 5. Music to my ears. Fantastic. And then we'll often be writing functions as f of x. That's going to be my go-to when I write a function. I don't have any on the board, but I was writing some before. And we'll also use g of x, h of x. We'll sometimes avoid I of x, but we'll do j of x, k of x, and just keep on going on in our alphabet. We do this to distinguish different functions from one another. Yeah, you had a question? Sometimes it does. Yeah. Sometimes we'll talk about things like, here we have d and t. Okay, this is the distance traveled by a falling object after t seconds. So we'll often use t for time as an independent variable. And then we might have d for distance, or a for acceleration, or v for velocity, or s for speed. We might choose letters just to make our functions more easy to understand and easy to distinguish from one another. But otherwise, no, the letter we choose doesn't have a mathematical significance, but it might have a mnemonic significance or a logical significance to us. And this is not, a common mistake will be to think, well, this is a function multiplied by x, because when I have f and I have a bracket, then I must be multiplying f by the bracket. No, that's not what we're doing. When I'm writing by hand, I will distinguish this like this, f, and then it's a little x down there. It's not like saying a times b. Okay, this is equal to a times b. This is equal to ab. But f of x, this is not talking about this is equal to f times x. No, no, no. This is a new way of writing f of x. This is a new way of writing y. It's a new way of saying this is my output. The nice things about it is I can change the letter to distinguish different functions. I can call all those three different lines, f of x, g of x, and h of x. And then I can also indicate the input value that I want to put in there. Okay? But here are some common functions. And we have a of r is pi r squared. This describes the area of a circle based on its radius r. So r would be my inputs, and area would be my outputs. And what shape would that make if I graph it, pi r squared? So it's describing the area of a circle, but if I put this in here to Desmos, you're going to tell me, oh yeah, okay, we see it, Mr. Jennings, I know. So instead of r, I'm going to use x because this is an x, this likes x and y, so I have area is equal to a pi. Oh, and then this is in the way of my keyboard here. How do I move this? There it is. So I have pi in here, right? 3.14. Yeah. 3 point. Oh, it is? Oh, there it is. Yeah, pi. Pi times x squared. There. So this is a function here, pi x squared, pi r squared. This is a function that tells me the area of a circle based on different radiuses. And it's a function because it passes the vertical line test, and because y is raised to the power 1. And it's just a parabola. Also, I would have a domain that does not include negative values for x, because we don't really think about a negative radius, a radius that goes into some other dimension. If we did, they would have positive areas. Okay. So we also have v of e is e to the 3. This is the volume of a cube based on an edge length e. So v of e, the volume is a function of edge length. And then d of t, distance is a function of time. So those are some different examples that we might have. So let's take a look at those linear relations. We could refer to the three lines as f of x is 2x plus 5, g of x is 2x plus 1, and h of x is 1/2 x plus 4. Now we have a robust system to describe different functions and talk about different functions at the same time. In this case, the x in f of x, we just replace it by 2. So when we want to have an input value of 2, you see when x is equal to 2, we write that as f at 2. So when I read this as f at 2 equals 9. So the x in f of x has been replaced by 2 to give f of 2. And how do I know that? Well, f is this function. I know I'm not talking about that function or that function because of this letter f. And when it says f at 2, I just input 2 for wherever I see x. So 2 times 2 is 4. 4 plus 5 is 9. So f at 2 is equal to 9. It's just telling you what to substitute when you do a substitution problem. Substitute and solve. Okay? And anywhere in the function where the variable x appears, we substitute a value of 2 in its place. Here, this function only has x appearing once. But if we look at the next example here, we'll see x is appearing twice. So we're going to need to remember that rule. Now, this is, again, talking to us about, we take this input x, we put it into our function operations, and that's given by all that stuff. F of x is equal to, and then we'll write an equation. Think of the equation like a vending machine or like some kind of machine that's going to transform those inputs into outputs. Okay? And it spits out the output based on the rules of math and Bedmas and exponent rules and trigonometric rules and all the different rules of math that we're going to have going from inputs to outputs. So our output is f of x, our input is x. We used to call y our output. Now we'll call the output of the function or the value of the function at certain points. We still graph it on the xy plane. So here's an example. We'll do the first one together, and then you'll do these two, and we'll check our work. Okay? So you're going to go to your handout. You're going to find this on the front page. On the right-hand side, so left-hand side over here. Did I see a hand up? Do you have questions? No? Okay. So I'll do the first one, and then you'll do the next two. So determine f at 0. So I have f of x is equal to x squared minus 5x plus 1. So f at 0, well, I write that as 0 squared, and I should substitute into brackets so that I don't make mistakes. 5 times 0 and plus 1. Okay. Notice every place that there was an x, I just put a 0. Okay. Now this is equal to 0 minus 0 plus 1. So then I could say, well, therefore, the function at 0 is equal to 1. And what that gives me is a point 1, 0. Okay, it's still an xy point. I could graph it. It would be this point here, a 1 in the x. Oh, so I'm sorry, I do this backwards all the time. I've warned you about that about myself, that I often invert my y's and my x's. Oh, and I have an eraser that does not work. Sorry. Here. This is x is 0, y is 1. So I can graph that as this point here. Okay? So that's the y-intercept of this function I've just found when I've calculated f at 0. Okay? So now I'd like you to try the same thing with f at 3 and f at minus 2. Remember, you're going to substitute those in for values of x, and then you're going to put them into the equation and evaluate. And then you're going to have a statement that's like, well, therefore, f at 3 is equal to something. Okay, go ahead and complete that, and then we'll take it up in... So let's take a look at the answers, because I did not push play. So here are the answers. We are on break, so I will see you in 5 minutes. So there's the answers for these substitutions. They're going to look like that. You want to just substitute in this value for every point x appears in this function, and then evaluate using Bedmas, and then you'll arrive at the same place we did. So what if we had a situation where we weren't substituting in a number, but we were substituting in some other variable, or even like a binomial here? We're going to substitute that in for x. Okay, so let's do this one together, and then I'll actually give you a second thing to substitute in for x, and we'll just have you do that on your own. All right, so over here, the way I'm going to tackle that is I just do exactly what I did with numbers, but in this case, I'm now substituting in like a binomial over here, or another equation, right? So over here I have I want to know what's g at 2x plus 1. So I'm going to copy down g of x. I wrote on my handout, so I'm going to do this on a blank piece of paper, is equal to 3x minus 2. And then I substitute into brackets. So now I have, well, what's g at 2x plus 1? Well, then I would have to say 3 multiplied by my input. My input now is 2x plus 1. And then I'm going to still subtract 2 because that's over there. And then I write out again, g at 2x plus 1 is equal to, distribute this, 6x plus 3 minus 2 equals 6x plus 1.
That's it.
Okay? And that's it. That's g at 2 of x plus 1.
How do you do GA?
G of a?
Yeah.
Well, there I would substitute a in for x. So can you do that in your head?
Exact same thing, just 3 at a.
Yeah. So I might do that, like that might be instructions I give to a computer. Take the number set a and substitute that in for x, for example.
The formula or the equation doesn't really change.
Right. What's that? Yeah, well, 1, I'm going to substitute 1 in for x, right? So that would be 3 times 1 minus 2 is 1. Sorry? Yeah, g at 1 equals 1, because 3 times 1 is 3, minus 2 is 1. So that will give us the point 1, 1. Oh, we just substitute a in for x. So if I'm substituting a, this a here, in for this x, sorry, this x over here, g at a, so over here I would have g at a is equal to 3, substitute into brackets a minus 2. Or I could just write that as 3a minus 2. Notice that the x just got substituted in for an a. All right? Yep. Well, that's what we're going to use as our input. So our inputs are x's. Oh, what would you put as a coordinate? You don't have a coordinate here. You still have a line. Notice that when I input this, I get a new function. It changed the function, actually.
So what do you do with that?
Well, that depends on what you're doing, right? So right now, I've been writing points over here. I didn't instruct you to do that. I was just saying that is a point, and I was reminding you that that's a point. This, on the other hand, is not a point. This is a new set of instructions. It's a new function machine. And sometimes you will have this notation. You will say, okay, well then g at 2x plus 1, that's a new function. It's a new function h of x. It's a new function. It's 6x plus 1 is h of x, and that could also be reached with this transformation of this other function. You'll sometimes see this later. Okay, we're not getting there quite yet, though. Getting a little ahead of ourselves. So now, I would like you to tell me, and I'll pause the video, and you can go ahead and do this one on your own. If g of x is equal to 3x minus 2, what is g at negative 3x plus 6? Okay, find that for me. We got to hurry up. All right, this one is, we just substitute in. This is equal to 3 at negative 3x plus 6. I just substitute this in for x there. Cool. And then I have to have my minus 2 as well. That's going to come down as well. And that's going to give me negative 9x plus 18 minus 2 equals negative 9x plus 16. Cool. And what is that? Well, when I do this and I have my equal signs coming down, and you don't see anything there, that is still there. I'm just not writing it out again because it hasn't changed. This is g at negative 3x plus 6. Okay? It's not giving me a point. It's giving me a new function.
Are we supposed to know how to plot that function?
Plot it?
Like, would you give a question saying, like, something, like, more difficult like that and saying, like, now plot this on a graph?
You can't.
It's not hard. No.
Can you plot?
What is it? Yeah.
Like,
I'll show you. This I can put this on a graph right now.
X plus 9 plus
Yeah. Here, we'll put it on a graph right now. It's g at whatever is equal to negative 9x plus 16.
Oh,
There it is.
so.
It's just a line.
Right. Okay, it just throws me off with the G and the.
Oh, sure. Yeah, I know.
I thought that was
It's
part of
it's
the line.
common to be thrown off by that when you first encounter function notation. Remember that that's just another way of standing in for y. It's just another thing that could be y. It could be giving me my output. Now, the machine that does the transformation of inputs of x into outputs, which are, in this case, g of negative 3x plus 6, the machine that does that transformation is here just a y equals mx plus b.
So if that's
It's just an
to
mx plus
help
b.
you figure out what the like point is or what the equation is. Like that's not part of the line.
Oh, this part over here, this
Yeah.
g at this?
So you just would picture that as y.
Yeah, if I were graphing it and I wanted to graph it, it might look like this, where I'd have a line with a slope of negative 9, like that, right? So that's a function, passes vertical line test. That's the point 0, 16. And I get that from this b, right? And the slope is negative 9. And I could label this then. This is g at negative 3x plus 6. And that's just labeling the line. But at that point, I'd probably rename that a new function. I would say g at negative 3x plus 6 is equal to h of x. And h of x is negative 9x plus 16. It is a new function. It's a different function than g of x, which was 3x minus 2. That was a line that went through here and had a slope of negative 3.
So when it's
That was g of x.
That's the x intercept. So I was gonna say when it's like negative 9x plus 16, how do you know where it crosses at that?
Oh, that's an mx plus b question. It crosses at the b.
Isn't that at the y?
Oh, where's the x-intercept?
Like, could you not know that?
Oh, the x-intercept I would have to evaluate this way. I would say y is equal to negative 9x plus 16, and I want to know when y is 0. That's going to give me my x-intercept. So I would say 0 equals negative 9x plus 16, and evaluate. And I would find that x is equal to 16 over 9.
But if you just drew a line like that would be fine. It's like kind of.
I'm just doing a sketch for your benefit. Yeah, I didn't ask you to graph it. Okay, I say we have to hurry up. We have to hurry up, and then we get these excellent questions. Okay, so now we've seen, and this will be on the quiz tomorrow. You want to be able to take a binomial and substitute it in for x to create a new function. You want to be able to do that. Or substitute in other variables, or substitute in values. And just get comfortable looking at a function notation where I have something like f of x is equal to that, and then I can substitute in these other values for x. And I can even do more complex substitutions. Okay. So let's carry on. Now we want to be able to translate these into coordinate points. What's that?
Oh, okay, yeah.
So we'll do the first one together, and then you'll do the next two, and I'll give you 30 seconds to do that. So here we go. It's on the back. Here you have f at 2 is equal to negative 1. So here we have a function, and when I input 2, it outputs negative 1. So I write that as a point this way. Put your inputs first and your outputs second. Okay. Go ahead and do the other two. See what you get. People need more of an explanation of that one? No? Okay, go for it.
What would happen if like it equals a binomial?
If it equaled a what?
A binomial, what would we do then?
Oh, if I had like a binomial there that I was inputting
Like on either side. Like,
on either side, oh, then I wouldn't be able to translate this as a coordinate point.
so would you just put like or,
Sorry?
Like if you gave us that on the quiz, I know you would, but if you did, like what would you want us to write?
If I gave you a question like this and I said translate it to a coordinate point, I would give you something that could be a point. I wouldn't try and trick you in that way.
Okay.
But think about like a point as being like one of the generators of a line, right? A point is a zero-dimensional thing. It has no dimensions. A line is one-dimensional. It goes off in one dimension, right? And it's a series, an infinite series of points all connected.
Okay.
So when I have something like y equals 2x plus 3, I can't say what point is that. That's like saying I make $10 an hour, so how much money do I have? I need to know how many hours did I work, and then I'll know how much money I have.
Okay.
right? So the line is all those infinite possible solutions to that. Lines can generate planes, two-dimensional space like x, y, right? And a line is only one thing inside that plane. Planes could be brought into a third dimension to create space, to create volume, to create three-dimensional things. And when we have that math, then we need a z coordinate that comes out of the board. And we can imagine planes cutting it or undulating like hills crossing it. And you could imagine you could create a video game that was three-dimensional, and you could define the terrain with different mathematical formulas. That's all coming later. But here we just have a point. So there we just have one point. I can ask you for a point. If it was a line or a binomial, I couldn't ask you for a point. It's not a point yet. So these are those. I take the input, I put it there. I take the output, I put it there. It's pretty straightforward. Now, you could also have a function like this, and I don't give you an equation. I don't give you a table of values. I just give you a picture. And then based on your ability to read the graph, you should be able to answer these types of questions. So, Camden?
No, I was going to answer.
Okay, so for A, Camden, go ahead and answer.
Well, would it be you go over on the the negative
1, 2, -3,
and then go to the line?
and then go find your function. Boop, there it is.
There it is.
And so what's that point? Let's label it.
-3, 3.
Yeah, this is the point -3, 3. So what's the value of the function when x is -3?
3.
3, yeah. So there, if I tell you the input that we have, you just go over to that point and find the function and read the value. So what's x when the function is equal to 0? When the value of the function is 0, what's x?
Is it at the
Nope.
0?
It's one of the zeros. So when is f of x 0? When is this function equal to 0? Aiden.
-5.
Yeah, it looks like -5. 1, 2, 3, 4, -5. Here's the point. X is -5. Y is 0. And so that's going to be, therefore, I could say, therefore, f at -5 is equal to 0. The function at the input -5 gives me an output of 0. F at 2?
2.
2, also 2, yeah. So there's this point 2, 2 over here. 2, 2. Oops, weird thing I drew there. And then, so that's f is equal to 2. And then what's x when the f of x is equal to 9?
6.
Yeah, it looks like about 6. I go up 1, 2, 3, 4, 5, 6, 7, 8, 9. And then go hunting for my x, which is here at 1, 2, 3, 4, 5, 6. Yeah, so that's the point 6, 9. Yeah, so that's, therefore, f at 6 equals 9. Okay, so that's reading off of a graph these types of things. So now let's do this question together. A cell phone company charges a monthly fee of $30 plus 2 cents per minute of call time. So we want to create a function in function notation that would do this. Do you have one already, Mac?
Yeah.
Yeah?
Well, originally I wrote c equals 30 plus 0.022.
Yeah.
And I did another one that is, I don't remember how to say it, but like c of t.
That's it. That's how you say
equal
it.
to 30 plus 2. Sorry, 30 plus 0.022t.
Yeah, that will do it. So here we want to recognize that we would have a line here because each the rate of change is constant. Every extra minute of call time adds the same amount to our bill. So as the minutes of call time grow, our bill grows as a line. So we're going to have something of the form y equals mx plus b. But we've wanted to do it in cost in terms of dollars of call time t in minutes. So I might have c of t is equal to, and then Mac tells us that she has 30 plus 0.02 times t. And that's a y equals mx plus b. It's just this one is b plus mx, which is the same thing. Doesn't matter what order we add it in. Camden?
What would you do about the monthly? Because if it goes up $30 each month.
So
Are you just
C
doing as of
is
1 month?
the C is the cost per month. So this is a line that tells me your cost per month. If I want to do cost per year, I would be multiplying everything by 12. And that could give me cost per year. And I'm never going to get around that cost per something. There's always going to be a time limit with these cell phone plans.
Okay.
But it's important to recognize that when I say this is cost per month, that per month is not a rate of change. It's not my M. My M is the per minute of call time. That's my per. And that the whole graph, the whole thing is representing time of 1 month. Okay? So I could graph that. It would, people are going to like memeify me. He's always saying, and I could graph that. It's going to have a y-intercept of what? 30. And a slope of what?
0.02.
Yeah, so it's going to climb very slowly like that.
So like by the time
It's
it
gonna look like
hits
this.
the 2 month mark, it would be at 60 automatically. Like, is that just how it would work?
No, you would have to use like an exact number of call minutes. You would have to have, what is that, 6,600 minutes?
Or not 60, but like
6 minutes. No, not 6. No, it's 2. No, 3. No, wait.
No, it's
1.5?
a different graph. Each month is a different graph.
150 minutes? 1,500 minutes? Yeah, 1,500 minutes to make it exactly 60. But it would be determined by how many minutes you talk. Yeah, so the number of minutes would be along here, your bill size would be along there, and this would be a good function for that. So what are the domain and range of this function? Domain, what is domain? Let's just review those definitions. What are we talking about when we're talking about domain?
X value.
All the possible x values for a function. Yeah. And then what's range?
The possible y value.
Yeah. All the possible y values of the function are the domain, the range. So here, D, domain would be, I have squiggle bracket there. X is a set of numbers such that X is of the, and, oh, I'm sorry. It's not X. Domain is a set of T values such that T is of the, what is T of? Are they going to charge you by fractions of the minute? Maybe it would be integers. Maybe they charge you by the minute, but not by the half minute.
Oh, so for the range it would be real numbers, and for the domain it would be.
It could be, yeah. We could have different number sets on inputs and outputs, yeah. And this might be an example. Now, how did we know that time was going to be measured in integers? We don't. They might charge you by fractions of the minute, and they might keep it to several decimal places. I don't know. Depends on the cell phone company. Maybe Fido's one way and Rogers is another. I don't know. But we could have a situation where T is of the integers. And what are some limitations on T? Alina?
It must be bigger or equal to 0.
Yeah. T is going to be bigger than or equal to 0. Greater than or equal to 0.
How to do that? Like, wouldn't it be 0.02?
No, because this is for time.
Because you can just have no call time in the whole month, and then but then
Yeah.
it's 0
Yeah.
or more than 0.
And we can see it from the way I drew the graph, right? I started my values of time right at that $30 flat fee, right at 0 for time. But I didn't include this negative line back here, because that's for if I talk for negative minutes. Somehow I'm like, I don't know, working for them or something, or getting my bill back. No, that doesn't exist. It's just brain bending to think about. So we don't have this over here. We only have this stuff going out that way. We could say that time is of the integers. If you said reals here, that's fine. And that time is necessarily bigger than 0, because you can't talk for negative minutes. But we have greater than or equal to, because you could talk for 0 minutes. And then your bill would be how much? $30, yeah, because C at 0, if I substitute 0 in for T, I get 30. So C at 0 is 30.
On the last one, do you think it was greater to or equal to, and then like have like another one that was like less than?
Oh, this one, is there an upper limit to T?
What must be the number of minutes in a month?
It would be the number of minutes in a month. That would be right at like September 1st. You at midnight you start your phone and you're talking the whole time, and you never stop.
So there will be a maximum.
There would be a maximum. Is it practical to write that down? Do we ever really need that?
No, but
You could.
How do we know when we're supposed to write it
If it's in the restraint of a month, wouldn't that be greater to the extent of the maximum time in a month?
Yeah, but how do you know when you need to do that? Well, in an application question like this, to be honest, I would never think about the upper limit. Would you really, like, as a mathematician, if you wanted to do something with this situation, evaluate different cell phone bills, ever think what would be the absolute maximum? Like, how long should I draw that line? Or would you just draw it for like a human sort of amount of minutes, like between 0 and 1,000 or something? I would kind of draw it 0 to 1,000. I would show a line going off to infinity, even though it doesn't go off to infinity.
Also, on the quiz tomorrow, do we need to like write these?
I like them written this way because that's what I taught you yesterday, but then people didn't watch the lesson and you got tutored by people who do it a different way. The different ways are also fine. I know how to read them, so if you write it in that way, I will still mark it that way, but you want a system. The one I want to teach today is still this way. The range, what's the range of possible outputs? C is a set of numbers such that C is of the... Yeah, this one will be reals because we definitely have decimals. As soon as I add 1 minute, I'm going to get $30.02. And are there limitations on C?
Yes. Minimum is 30. Greater than or equal to 30.
Yeah, greater than or equal to 30. And yes, there isn't a hypothetical upper limit that happens if you leave your cell phone running all month. But in that type of situation, probably you call the cell phone company and say there has to be some kind of error and they refund you that money. Like that never happens. So is there an upper limit? Yeah. But I'm just not thinking about it in this situation. Like I really don't think I'd ever need to know that upper limit. And if I did, I'd just do the math. Okay, well, there's how many minutes in a day, and there's 31 days in a month, and then there's my upper limit. But I'm not thinking about that at this point. This is totally satisfactory to me. I don't think I'd ever need more information than that. So there's only one other topic, and there's going to be covered on the quiz tomorrow. And I want to give you an example, and we'll practice it right now. I'm going to have a new function here, and it's f of x is equal to 6x minus 3. And I want to know if f of x equals, let's say...
Is there a section for this in the booklet? Or is this like a new page?
This is a new page. I just realized that we don't have an example like this in the PowerPoint. So I want to give you one example that we do together. So if I have a function f of x equals 6x minus 3, and I want to know when is that equal to 21. Can you find me x? It's not 1.
Did you have to substitute 21 in somewhere?
So I do substitute 21 in. I substitute it in exactly this way for f of x. Okay? So the value of the function for some value x is equal to 21. Gavin?
4.
X is equal to 4. So if I substitute in x is equal to 4, I have 6 times 4 is 24, minus 3 is 21. Great. So x is 4.
Is there like an actual strategy for that?
Yeah.
Or is it like a process of elimination?
So did you do that by process of elimination or algebra?
I just did 4 times 6.
Yeah, so you looked at it and you were like, it's got to be 6, right? Yeah, good. So that's like using a table of values, guess and check method, totally valid, but we can use algebra. Alina?
If we write down 21 equals to 6x minus 3, then the plus 3, so 24 equals to 6x, and then divided by 24.
There's our algebra method. Okay. We could also graph it and use a graphical method. Probably the slowest method because we need to be very accurate. But our graph would look like this. I know that a line 6x minus 3 will be very slopey, and it's going to grow like that and go down like that. And then I say, well, I'm going to go up here to 21 and go across and find for what x value does that equal. And that would be the point for 21. That would be a graphical method. Yep. Oh, over here, 21 is equal to 6x minus 3. Add 3 to both sides. Yeah, great question. 24 is equal to 6x. There, boo boo. People are asking, where did the 21 come from?
Yeah.
Oh, it came from here.
Oh, so it's just random.
Yeah, well, it's not well, it's somewhat random. It's,
Or like-
it's the question your math teacher gave you. Okay, if I have this function and I tell you that it's equal to 21 at some point, which it is equal to 21 at some point. I chose a function with an unlimited x and unlimited range and an unlimited domain. So then to solve that, you substitute it in as the value of the function. Okay, so that's like telling you, here is the y value. Tell me the x value that will produce that y value. If I tell you the value of a function and I ask you to give me the input that creates that value, then that's how you do it. All right, so those are all the topics about function notation. The next thing would be to move on to some practice problems. I feel that we spent a long time discussing domain and range, and I should have probably just repeated the lesson from yesterday.
So we're not doing some maximum and minimum of quadratics is not on the.
Do people have an? Oh, I'm gonna pause this now. So thank you for showing up for your learning, and that's a function.